My name is Jim Willsey. I'm with Spellman High Voltage. For those of you that don't know who Spellman is, one of the larger manufacturer and designers of high voltage DC power supplies. So we build, the turnover we do annually, about 60–70% is some form of X-ray application, and obviously industrial X-ray is a big part of that. Fred asked me to do a white paper, and I had to call on some colleagues for assistance. Our colleague, Boris Sasic, contributed greatly to the presentation. He was not able to attend, but Sam Pindrys, one of my colleagues for better part of 16 years with 2 companies, contributed greatly as well, and then I had to kind of tie everything together. X-ray tubes and generators work together to provide performance and reliability in today's more demanding industrial applications. I think that's, when you look at the kind of stuff that VisiConsult's doing, and I'm sure the other presentations, you can see that, the X-ray source has to evolve along with the technology in the industry, and Spellman is a very big part of that as well. Materials and processes in X-ray tube manufacturing have greatly improved performance and reliability. If you look at the X-ray tube design and the physics of it, not a lot has changed in 100 years since the first X-ray tubes, but the materials and processes and the way they're able to build them for better performance and reliability has certainly improved, and the generator has to follow suit. 2 distinct forms of generator we're going to talk about today are monoblocks. With the monoblock, you're taking the high voltage section along with the X-ray tube and the power conversion bits, and you're putting them all into one package to create a turnkey X-ray source. Well, not necessarily turnkey because they don't have all the controls, but it's an X-ray source in a box more or less. There's a lot of value to the monoblock because you eliminate long high voltage cables and things like that. There are also challenges which we'll discuss. The X-ray tube has a useful life, and the generator should perform and operate in order to protect the tube and prolong the life. A lot of people make the habit of calling an X-ray tube a light bulb. I never use that term because there's a whole lot of technology in there. Spellman really understands the importance of operating the tubes at the highest performance possible and helping to prolong their lives. And although the basic operation of the tube is straightforward, choosing the right generator can really enhance the performance and add value to the application. The presentation might at times seem a little tube-centric. It's because we have to discuss the X-ray tubes and how the generator, we feel, really enhances the performance. So, if you look at typical X-ray tube end-of-life failures, there's really 2. These are the common ones. You have arcing. Everybody knows what arcing is. And then filament burnout. These are the things, in the useful life of the tube, these are the things that are eventually going to happen. Could take a year, could take 10 years in some cases, depending on the duty cycle. X-ray tube arcing, basically primarily due to tungsten evaporation, where it metallizes the X-ray tube envelope. So the surface conductivity increases and eventually causes arcing to the tube wall. In the case of a glass tube, that can puncture the glass, causing permanent damage to the tube. If you look down here, here's an X-ray tube arc that caused a puncture in a glass tube, and that's shot. That'll never be used again. All right. So X-ray tube arcing is predominant in X-ray tubes, continuously used close to their maximum voltage ratings. Typical usage and duty cycle, as I said, will play a part in determining the useful life of the X-ray tube. But on the power supply side, both passive and active circuitry are designed into the X-ray generator to manage those arcing events and minimize premature failures due to arcing. But in arc management, this is the active circuitry side. The arc management is done through DSP control, and it's all programmable in the generator depending on the tube, the peak arcs within the tube. Arcs are sensed by a current transformer in the high voltage feedback loop, and then the generator must react to an arcing event in less than a microsecond to quench the arc. So if you let the peak arc go as high as it wants to, it could easily damage the tube, so you need to turn it off quickly. Here, the arc detection is scaled to kV program value. The arc sense voltage is fed to a comparator on the system control board that is scaled to the kV program reference level. Right, so you're looking at the peak arc current and the kV. And this scheme enables the generator to avoid false arc detection, and micro arcs are virtually ignored in this scheme. Then the signal is received and latched in hundreds of nanoseconds. That's how quickly this is all happening. We're probably going to have to go back to this slide a couple times, to go through things. But basically, this is an example of an arcing event. You have your ramp up. You're making X-ray. An arc is detected, and the generator quenches the arc. There's an arc quench time. The generator has a decision to make whether it's met the arc count maximum. If it has not, then it will ramp up the kV again, make X-ray, and then the next arcing event, it will have to go through the same process. In this scheme, the arc quench is set through user settings, anywhere from 50 milliseconds to 1 second. The arc count threshold, okay, so the number of arcs that are going to be allowed to occur before the generator just shuts down the tube and says there's something really wrong and we don't want to go any further. That's also set through the user settings, anywhere from 0 to 30. I made a typo there. That should not be 30s. That should be 30 times. I apologize. The arc count value of 0 disables the arc count function altogether. Not recommended in an OEM application or an application where you want to protect the tube, but it's good for testing. So it can be used for diagnostic purposes, allowing the arcs to continue so you can, so you're not shutting down the generator every time there's an arc. The arc current is sensed, enabling a rollback, which is really the start of that quench. So you're making X-ray, it senses the arc, it rolls back, the kV goes down, and then it times out. The DSP first increments an arc count. If this is the first arc and the set threshold is greater than 1, it'll ramp up the kV again. And it'll continue doing that. So then the microcontroller arc time is the duration of the rollback. And it will time out, and the DSP will re-enable the kV output. And this sequence will continue until the number of arcs detected exceeds the programmed arc count value. So by protecting the tube from these arcs, as quickly as this, you can definitely prolong the life of the tube. Doesn't mean there's not a problem with the tube. Maybe it needs seasoning, or maybe the tube has failed. But the bottom line is the generator is not going to contribute to that due to not reacting to the arcs. The next common tube failure, or end-of-life failure as we call them, is X-ray tube filament burnout. As tube voltage decreases, the filament current increases, and you can see that in these graphs here. Each one of these curves here is kV, and as the tube voltage decreases, the filament current will increase. As a result, the filament temperature rises, and this accelerates the filament evaporation, or the tungsten evaporation that I referred to earlier. So 10% reduction in filament wire mass is considered to be the practical end of the filament life. It doesn't mean the tube won't work anymore, but you're going to start to see performance take a dip. Abnormal X-ray tube failures, ones that aren't always, the normal life of the X-ray tube, being a consumable product, you'll have the arcing and the filament failure, but abnormal ones are ones you don't plan for. And if the filament current ramps too quickly, but the filament doesn't reach operating temperature, you're going to have a problem. So if you look, this is your filament ramp here, and this is your MA. MA rises quickly, but it's not controlled as defined by the MA ramp, and it forces the filament current to go to max because you haven't reached the proper operating temperatures. The higher filament stress over time contributes to premature failures of the tube, increased tungsten burnout. Preventing this is as simple as, the filament current rise time is controlled within filament thermal properties. The filament reaches the operating temp by the time emission control activates, and the result is a well-defined current rise as intended. There's your filament ramp, and there's your MA. And that's more what the tube manufacturers want to see with the generator control. In the case of AC and DC filament power supplies and their effect on filament settings, particularly AC filaments, your high voltage cable length can have a great deal to do with filament calibration settings being off. So typically an AC filament is going to be calibrated to or designed to a certain tube length, maybe within 3 to 5 meters or something like that. If anything longer is used, it's important to understand that so that the filament can be recalibrated to that cable length. And this happens all the time in the OEM world. DC is there's less calibration involved, but you have to. You want to take that one?
Basically, the most important part about filament is not to exceed the manufacturer's max current. So it's very important that no one setting of the current is for every tube. So each tube should be calibrated with the length of cable and not to exceed the max current for your application. Actually try to lower the max setting if you don't need the emission current or the tube current at the maximum levels. Try to set it 10% lower for the max filament current settings. This way it will extend your filament life and your tube life. Okay, so always calibrate it every time you change a cable or you change a tube and so on. Okay, especially for AC filament.
There are ways of optimizing the X-ray tube settings, and in some of Spellman's power supply designs, we actually have a graphic user interface where those filament settings can be input manually. So you can put in things, KV ramp rate, obviously max KV, MA ramp rate, and then all the filament settings. And this takes a lot of the questions out in operation. So this is a very useful tool for a lot of OEMs that use it regularly. Maybe some of the things that can be set within the GUI and the ranges. Okay, so KV, MA, filament, large and small. Okay, all useful in the OEM world or even the end user world. Then there's auto loading of settings. So through the GUI, tube settings can be automatically loaded from a drop-down menu. So all those settings from that previous screen can be loaded right into the generator, depending on the tube that's selected from there. And this is just one example. I mean, Comet and Varex, build a lot of tubes, but we power thousands of tubes. And then new tubes that are not in the drop-down can be added and stored for later use if necessary. Auto tube seasoning profiles are also a benefit of being able to download those tube settings. So you select the tube from the drop-down menu, and you get all the seasoning profiles along with the manufacturer recommended seasoning profiles. Okay, whether they be daily, weekly, or monthly. And then, of course, new and custom profiles can be added and stored even for tubes that are already in the database. This section is more specific to monoblocks, the HV insulation. All right, so in monoblock designs, considerations around maximum electric field and field control techniques are critical. We say it in the high voltage power supply business. Every morning you wake up, you're in an arm wrestling match with the forces of physics. So now you're doing that on the generator side, but now when you're building a monoblock, you're actually forced to do it with the tube and the integrated package as well. So inadequate electrical stress control can easily result in premature failures such as glass punch through. And here is an example of just a single arc. As you can see, there's no carbonization around it. It's just a single arc that, as a result of poor electric field control, just punched through in the first arc. Okay, that's something you definitely want to avoid. High voltage insulation continued. Inadequate E-field modeling causes charged particles to etch the glass. Okay, you can see there's an etch right there. And obviously these spots here and those That's all as the result of poor E-field modeling. Leakage current increases as a result, causing errors in the output current measurement. A decrease in X-ray dose occurs even though the tube current appears to be well controlled, so that leakage current is actually contributing to the current measurement. And this failure mode could take weeks or months. And if you're a monoblock or a generator manufacturer, that's usually right about the time it gets into the field. So you don't really want that one. So we try and catch those well before they leave the factory. Thermal management is another one, particularly with monoblocks. All right, so X-ray tubes are very inefficient. I don't think anybody in the room is not aware of that. So, but less than 1% of power is emitted in the form of X-ray. Okay, that's about as inefficient as it gets. Heat losses need to be well managed to prevent high temperature rise, which I'll go into detail. We've already gone into some of the details why, but we'll go into more. The dielectric oil possesses, the optimal combination of electrical insulation and thermal properties, but it can't do it all. Here you have an X-ray tube operated in a hot oil environment that's actually discolored, carbonized. Okay, definitely not something you want. The effects of poor thermal management. Higher internal temperatures increase filament evaporation. Again, we've already discussed that at length. Not desired. Higher glass temperature plus burned oil equals greater X-ray filtration. So your X-ray spectrum actually changes. Focal spot melting is another result of excessive heating. Focal spot size increases. X-ray spectrum becomes harder. And then this, of course, increases evaporation, leading to shorter tube life. Tube dose stability, another one. Detector technology is driving the need for higher quality X-ray sources all the time, and this is literally happening in real time. X-ray dose stability is greatly dependent on tube temperature. And tube temperature drift can be greater than 10% in some cases, as you can see by that graph. You design to improve dose stability. So a combination of analog temperature compensation along with digital characterization and compensation, drift can be minimized to negligible levels, and you get something more like this graph here as compared to the one on the previous slide. All right, so in conclusion, as industrial imaging technologies evolve, X-ray source requirements become more and more demanding. Again, we see this more and more every year. The best X-ray tubes on the market still require an exceptional, sophisticated generator for peak performance. I don't think anybody would deny that, even the tube guys. X-ray generators designed to enhance the tube performance and play a role in protecting it over its useful life should always be a major consideration when choosing. So in short, an X-ray generator designed with reliability, serviceability, flexibility, simple integration, combined with the low cost of ownership is always going to add value to the imaging chain. And that's what we feel we do at Spellman with many OEMs. And that's all I have. I can open up the floor to any questions. That's why I brought Sam for the most part.
Yeah, if anybody has specific questions that you experienced with a X-ray generator or a tube, I'll try to help you. Yeah.
We have an X-ray tube that is in a bay that can hold the maximum amount of radiation. So we had to set an electronic limit on it. Is that bad for the tube to not warm it up to the full power rating on the tube?
I would recommend warming up to full power. Actually, it extends the life of the tube.
Full power and
Yeah.
full kV?
Yeah, full kV. Mm-hmm. Any other questions?
Maintenance of the high voltage cables.
Yes.
We've had issues, too much grease, not enough grease on the end of the cable. Is there a recommended?
Everybody has their own recommendation. I'll give you mine.
Yeah.
So, well, first of all, what type of cable you have, because there's very different types: spring-loaded, non-spring-loaded.
So with the clamp on the end of the tube.
The clamp, I would not recommend that one. The-
Not a fan.
Not a fan of, because it's very hard to control the pressure. What I would recommend is the new types spring-loaded, and they're consistent, and they also adjust to a variation in temperature. So you could extend your maintenance from 3 to maybe a year to 6 months, versus on a pressure type where you adjust the gapping. Those you have to check every 3 months, maybe sooner, if the environment fluctuation in temperature is a great deal. And I would recommend the spring-loaded and not use the handle type. It's convenient, but it doesn't help you save or reduce the number of arcs after a period of time.
We're doing it on a monthly basis, our maintenance, and we've ruined
Well,
several hypo machines.
Well, yeah,
That gets expensive.
yeah. So I would recommend going to spring-loaded type cables. Mhm. Okay.
You talked about calibrating after changing cables.
Yes.
Is that a practice that you guys have any information on, a template or technique or?
How to calibrate a filament? Is that the question?
To the cable length.
Yes. Typically AC, for AC filaments, if you change the length of cable, you need to recalibrate every time. For DC filaments, which are mostly Spellman type power supplies, but not all of them, the likelihood you don't have to adjust unless the cable length is over 20 meters or larger.